to current slide. Oh, yes, there we go. All right. Now, before the day is over, okay, hopefully before anybody leaves, we need to decide what day and time would be best to try to make up Tuesday's class. I meant to do this last Thursday and completely forgot about it because it was my fault that the class was missed. I had a doctor's appointment. I couldn't avoid it, but I don't want y'all to miss out on math that you paid for, and I know you would be very upset if you did. So think about, and I put it in the announcement that I got. Did y'all get the announcement? Okay, good. So the times that to consider are Mondays or Wednesdays. Well, let's start with this week. Today, if you wanted to, we could do it right after this class. I have that period free. I could do it between 12:45 and 3:15. There's a block there. So that's Tuesday and Thursday, from 9:45 until 11:30 and 12:45 until 3:15. 2 blocks each day. Friday, I've got 8 to 12 on Friday. We could make it up then, anytime, early, late, whenever. Okay? Okay. I do have a meeting this Friday on the Birmingham campus, but I believe it's around 11. So early I could do it. Okay? Now, Monday, either 8 to 10 or 3:45 until 6. Either of those times. And Wednesday, 8 to 10. So be thinking about what time would be best, and we'll do the time that's best for the most. I'll record it so anyone who can't come during those times can pick it up off YouTube. Don't close it all the way because they didn't unlock the door. Okay. Thank you. And I've got to find you. Cassidy, right? No, I'm sorry. Huh? Cammy. I said the wrong name. No, you're right there on that same. There you are. Okay. All right. Anyone else come in since I called roll? Okay. So, be thinking about when we can make up the test. All right. Any other questions before we get going? I mean, not the test, the class. Any other questions? That's what the option is. I sent that email or the announcement on Blackboard. Yeah, for the class we missed, because that was my fault, not the school's fault. So I wanted to be able to make up that class whenever would suit best. And the days and times are today from 9:45 when this class is over until 11:30. I have a free period there. And from, what did I say, 12:45? Yeah, 12:45 to 3:15, I have free block there. That's Tuesday and Thursday. Friday, tomorrow, 8 to probably something like 11. I have a meeting, I think, around 11 tomorrow. So anytime between 8 and 11, we could do it then. On Mondays and Wednesdays, 8 to 10 in the morning. And on Mondays, only 3:45 until 6. So pick the time or times that would be best for you. And we will. And if you can't make any of them or can't make the time we choose, then it'll be on Blackboard. On Blackboard through YouTube videos. And why am I not able to find anybody's name this morning? Janae is here. All right, good deal. All right. So be thinking about that. We'll decide that when more people get here, but before people start leaving. Okay. Now, if any questions on math part? Everybody got your quiz? Quiz 2? Anyone did not get quiz 2? All right. All right. Chapter 2, polynomial rational functions. We're still in the polynomial part. We're almost through with this. And we're in section 2.4, complex numbers. Now, if you go back and review the syllabus, you'll see there's no mention in the course description of complex numbers at all. Now, maybe that was an oversight, or maybe they just figured it was going to be incorporated. But since they didn't mention it, I'm not going to test you on it, but I do want you to be aware of this and how it affects what we're going to be doing the rest of the chapter. Okay? So let's do a quick slideshow of complex numbers. You're not going to be tested on this, but you will probably see it possibly sometime in the future. Okay? Especially if you go in upper level math courses, you will see it. If this is your terminal math course, there's a good chance you won't run into complex numbers that much. Now, they'll say use the imaginary unit I. Okay? That's a strange little number, I. We'll talk about it. To write complex numbers. We'll add, subtract, and multiply complex numbers. Then there's a thing called the complex conjugate. Now, it sounds like a big, hairy, mystical word, but you've been using everything except the complex part. You've used conjugates before with probably not knowing that's what you're using. But we use complex conjugates to write the quotient. Notice here, they didn't say anything about dividing. You have to use complex conjugates to get the quotient of two complex numbers instead of the form. And we'll find complex solutions for quadratic equations. That's where you'll run into it in perhaps exercises or other things you do for this course. I'm going to try not to test you on that. So let's start with the imaginary unit I. I want you to meet my friend I. Okay? Isn't he cute? You know, you can't see him. He's no, I'm just kidding. Okay. What in the world is that? You've learned that some quadratic equations have no real solutions. Remember those that when you plot the parabola, it never crosses the x-axis. Okay? They're either above or below, but never crosses. Okay? Here's one of them. This quadratic equation there. Can anyone give me a solution for that? A value for x that makes that true? Anybody? You win a huge math prize if you can come up with that at a real number that will make that true. There is none. None whatsoever. No real number. Can you square it? Because when you square a real number, it's always non-negative. And Tyler Weehans here. Okay. And it's non-negative. You add a non-negative number to a positive number, guess what? It cannot be zero. Okay? There's no real solution because there's no real number that can be squared to produce a negative 1. That would have to happen. To overcome that deficiency in our mathematical system, mathematicians created an expanded system of numbers. So let's do a timeout here. Let's go back to grammar school, maybe even preschool. And what's one of the first things you learn to do in math? Count, okay? And we use what they call the counting numbers. 1, 2, 3, 4, 5, 6, 7, 8. Those are the counting numbers, okay? There's another name for them. I think that's Shalonda under all that. Is that right? Okay, good. All right. All right. And there's Karen. All right. So we started off with the counting numbers. There's another name for the counting numbers. Those are the natural numbers. Okay? Now, at some point, we added one other little number. Not much value, in fact, no value at all, but we added one little number to the counting numbers. Anyone know what number that was? 0. And we add 0 to the counting numbers, and James decided he would show up today. That's good. Okay. What is it? James didn't show up last time, right? Oh, good. Yes. Okay. Were you the only one?
Oh, no, not declared.
Oh, okay. All right. Okay. When you add 0 to the natural numbers or counting numbers, we call that set the whole numbers. 0 plus the counting numbers or natural numbers. And then after some point, let's say I don't know which you did first. I imagine the first thing you did after that, you could add and you subtract and you could multiply those natural numbers, those counting numbers, those whole numbers. But then someone wanted you to divide those whole numbers, those counting numbers, those natural numbers. And guess what? Then you ran into fractions. The fractions introduces what we call rational numbers, the ratio of two other numbers, okay? And that rational number, and we'll keep them positive for now, that was what we call fractions. You could also express those as decimals, especially if the decimal repeated itself or terminated, like 0.5, 0.75, 0.125. Or it repeated itself, like 0.333333333. That was a rational number. Okay. Now, probably in the middle of all that, we introduced, or someone introduced, for you it would be negative numbers, okay? Negative numbers were take the whole numbers and negate them. Take the whole numbers and negate them, okay? And that made negative numbers. What's the set of all whole numbers with their opposites? Called the set of integers. Okay, so we have a new set of numbers, integers. And now, when you have those rational numbers, they can be positive or negative. So that made the set of rational numbers. But at some point along the way, you ran into square roots. And for instance, the square root of 2, is that a rational number? Okay, don't pull the door all the way to, that didn't unlock it. Okay. Here's Sharona. Okay. So, we have a problem there. We have some decimal numbers that never repeat. Ever repeat any set of digits whatsoever. And those are also numbers that cannot be expressed as a ratio of two numbers. And since they're not rational, we call them irrational. Okay? Now, when you take all those together, the set of counting numbers, whole numbers, integers, rational numbers, irrational numbers, put them all together and you have this, what we call the real number system. Real numbers. But that's not them all. Okay, that doesn't count everything because there's no real number that will solve that. So here we come up with our imaginary friend here, I. That imaginary unit, they call it, is the square root of -1. Now, up to now, you've been told you cannot take the square root of a negative number. And you can't in the real number system. But you can in what they call the complex number system. Okay? And we introduce this little entity here, I is equal to the square root of -1. This enables us to deal with situations such as this, and many more. I forgot to mention, also some other irrational numbers would include things like pi and e. Those are also irrational numbers. They're not rational, can't express as a ratio of two integers, and the decimals go forever without repeating. Okay, so let me get back to this. I, if you squared both sides here, you get I squared is equal to -1. So these are the two expressions of that imaginary unit I that you would need to know in just about anything you did with imaginary numbers. The I is the square root of -1. It's an imaginary number. It's not a real number, but that's what it is. And when you square that, I squared is -1. So now we do have a solution for that, but not in the real number system. Okay. Now, by adding the real numbers to real multiples of this imaginary number, now we get a new set of numbers called the complex number system, the biggest group of numbers we have. every complex number can be written in a standard form of A plus BI. A is a real number part. B is a real number, but it's multiplied by that imaginary unit. Okay? So, all real numbers are complex numbers because B can be 0. Okay? Those are your real numbers are all complex numbers as well. But now we've got the possibility of imaginary parts. So let's see what happens. What if you had a complex number, or you did an exercise, and you'll be doing some, you come up with -5 plus the square root of -9. Well, square root of -9 you can't do in the real number system, but what you can do here is factor out, let me get my pen set up, okay? What you can do with this is make that the square root of a -1 times the square root of 9. Okay? Now, what's the square root of -1? Do I need to go back a slide? I. Okay? And what's the square root of 9? 3, so this becomes 3i. So this becomes -5 plus 3i. That's in standard form. Real number plus real number times I. Okay? And they've done the same thing here. They put the 3 in front, which is fine. And that's where it usually goes. That's the standard form, A plus BI. So here's the definition of a complex number. Let A and B be any real numbers in the world. Positive, negative, fractions, decimal, rational, irrational, doesn't matter. The number A plus BI is a complex number, and it is said to be written in standard form if that's how you write it. Okay? The real number A is called the real part of the complex number, and the real number B, and this is where I don't quite do it this way. They say the real number B is called the imaginary part. In my mind, BI is the imaginary part. They say it's just the number B is the imaginary part. Seems like you would include the I with it to make it imaginary. Okay? When that B is equal to 0, though, there is no I then. Okay? And that number is a real number. A plus BI is a real number, but B is 0. Okay? And A is a real number. When B is not equal to 0, the number A plus BI is called an imaginary number. Okay? Now, and that's a good name for it too. A number of the form BI where A is equal to 0, that's called a pure imaginary number. Okay? So it's sort of nitpicky on terms here, but that's what we mean. Again, you're not going to be tested on this, so don't sweat too much, but in case you ever run into it again, you've been exposed to it, like the flu. No, nothing like that. So here's how we set these up. The set of real numbers is now a subset of complex numbers, okay? The imaginary numbers, which the B is not equal to 0, these are real numbers versus imaginary numbers. There's nothing in common here, but when they go together, that forms what we call complex numbers. This is true because every real number A can be written as a complex number, A plus 0i, okay? So that is a complex number as well. But usually if it doesn't have an imaginary part, then we just call it a real number. Okay? So I think we beat that horse to death. Okay? Any questions so far? And again, you're not responsible for this. Now, what do we mean by two complex numbers being equal? Okay? If you have A plus BI, that's a complex number, and C plus DI, that's a complex number, both written in standard form, real plus real times I, okay? Both are there. They are equal to each other. A plus BI equals C plus DI if and only if A is equal to C and B is equal to D. Otherwise, they can't be equal. You can't flip-flop, you can't change signs, Can't do anything. They must be identically equal to each other. That's what we mean by equality of complex numbers. Okay? Operations with complex numbers. To add or subtract two complex numbers, you add or subtract the real parts and add or subtract the imaginary parts, just separately. It's just like they were like terms. The real parts are like terms, the imaginary parts are like terms. You combine like terms. So if you have two complex numbers, a plus bi and c plus di, written in standard form like they are, the sum and the difference of those are like this. A plus bi plus c plus di is a plus c, that's the real part, b plus d times I, that's the imaginary part. Just add the reals, add the imaginary. See, that's why I like to call this the imaginary part. You add the imaginary part and you get that. Now to do the difference, you just distribute the minus sign across here and add, just like we always do. So this would be a minus c is the real part, b minus d times I, that's the imaginary part. Okay? Just like you would expect. It's just like adding two binomials. If you have two like terms here, add those. Two like terms here, add those. Subtract them, whatever. Just like that. There's nothing really new here except that little I, that imaginary unit called I. Okay? But except for that, just as normal. Okay, everybody got it? We're still writing? Okay. Any questions so far? All right. Just as in the real number system, there is an additive identity in the complex number system, and it's the same one, 0. Okay? If you add 0 to a real number, you get the same real number. If you add 0 to a complex number, you get the same complex number. Okay? So, that's just the number 0. 0 plus 0i. Okay? 0. Now, there's also an additive inverse of a complex number. In the real number system, give me a real number, any real number in the world. Okay? 1. Okay? What's its additive inverse? Negative 1. You add 1 to negative 1, you always get 0. Well, what's the additive inverse of a plus bi? Any old complex number in the world. You just negate it. And that would become negative a minus bi. Okay? That's the additive inverse. Because if you add the number to its additive inverse, a minus a is 0, b minus b is 0 times I, and that just comes out being 0. And here's the quantity. If I can find you. I know you're in here. There you are. All right. So, the complex number system has an additive identity, 0, additive inverse. It's just a negative of whatever complex number you were dealing with. Okay, and of course the additive inverse of 0 is 0. Nothing new there. Now, we're not going to do these, but they're really easy to do. And I guess we will do them, but you just add the real parts. 4 plus 1. Oh, they haven't gotten the answer yet. It's going to be 5, and then 7 minus 6 is plus I. So 5 plus I. It's just that easy to do. You don't have to take all those steps, but there's your answer, 5 plus I. Okay? A little bit more, not much. 1 plus 3, 4. 2i minus 2i is 0. This answer is just going to be 4 then. Okay, I said we weren't going to do them, but I'm not going to write them out. I'll put it that way. 4 plus 0i, you don't have to write 0i. You can just write 4. Okay? Again, you're not responsible for this. It's really easy stuff, though. How about this one? we have a pure imaginary number, no real part, that's fine, minus this one, minus that one. So what would we do? Let's deal with the reals first. No real part here, that's a 0 for real. What do we have here? A plus 2, minus 2. So there's no real part in your answer, okay? Imaginary part, 3i, minus 3i, that leaves to 0. But here you have a minus 5i. So it looks like our answer is just minus 5i. And let's see what we got. Yes, that's it. You don't have to write that 0 down if you don't want to. It's perfectly fine. A pure imaginary number. Oh, there's another one. All right, this has a string of them. Now, you can work it out the way they do. That's fine. But all you do is take the real parts. 3 plus 4. 3 plus 4. Minus 7. 0 on the real part. The imaginary part. 2i. Minus I would be I. Minus another I would be 0. This is just 0. All that equals nothing. Okay? 0 plus 0i, which is just 0. Okay. It says here, many of the properties of real numbers are valid for complex numbers as well. In fact, I can't think of any that aren't. Okay? Here are some examples. Associative properties of addition, sure. Doesn't matter which, how you associate them, they work. Multiplication, yeah. Associative properties of multiplication, that works. Commutative properties of addition, yes. Doesn't matter which order you add. And commutative properties of multiplication, doesn't matter. Now, we haven't told us how to multiply yet, so don't get too bent out of shape over that yet. It's easy. Distributive property of multiplication over addition, absolutely. They just haven't told us how to multiply them yet. But we'll get to that. Okay? Notice how those properties are used when two numbers are multiplied. That's why they said the properties first, and now they're going to tell you how to multiply. Now, they're doing it one way. I'm going to show you, I think what you already know is the easier way to multiply. Good old FOIL. Because these are just like two binomials, right? And complex numbers are always going to be either monomials or binomials, okay? They can't be any more. So it's pretty easy. So you do the first, A times C, AC. There it is. Okay? Now, you can do the other two the same way we normally do. Outer, that would be A times DI plus B times CI. Well, those are both imaginary parts. That's outer and inner. So that's AD plus BC times I. However, when we get to the last part, what do we have? B times D times, what would this give? Here's our calc. Okay, good deal. Okay, what does this give you when you multiply these two together? I times I, what's that? I squared, and what is I squared? Okay, -1, exactly. There's the big difference here, okay? Your first and your last are both going to be real. Your inner and your outer are going to be complex. The difference is the product of your last, B times D, plus BD, times a -1 would be minus BD. So your final answer is AC, real, minus BD, real, plus AD plus BC times I. So that's how you multiply. Just simply FOIL, okay? Knowing that the first and the last are going to wind up in the real part, you just change the sign of the last one, and the middle parts, the inners and the outers, are going to be your imaginary part. So it says, rather than trying to memorize the multiplication rule, you simply remember how to use distributive property. Now, you don't need that. Just FOIL it, and it works. Okay? It works. Okay. This one is a monomial, a real, multiplied by a complex number. What would that give you? Negative 8, isn't it? Negative 8. Whoa, wait. 5. They're going to take your time. Negative 8 plus 12i. That's going to be the answer, right? Negative 8 plus 12i. It's that easy. Sorry about that. I wish I could make it harder. Haven't figured out a way. Now this one, you'd have to FOIL it. Okay? 2 times 4 is 8. Let's jump to the last. And minus I times 3i would be, minus I times 3i would be negative 3i squared. Well, what's I squared? Negative 1. So that would be negative 3 times negative 1 is plus 3. So 8 plus 3 is 11. There's the real part. Okay? Do the imaginary parts. Minus 4i plus 6i. What's that? Plus 6i minus 4i. It's not that hard. Plus 2i. There's your answer. What did I say? 11 plus 2i. Let's see if we can get it. You can do it their way. It's perfectly fine. Perfectly fine. Perfectly fine. Perfectly fine. But it's so much easier to do it boiling it. Okay? So, but again, I'm not going to expect you to do these necessarily, but if you ever run into them, you now know how to multiply complex numbers. Okay. Oh, here's another one. Now, notice what happens here. Remember, your first and your last both give you real parts. So your first part gives you 9. Your last part gives you negative 4i squared, which is, again, plus 4. 9 plus 4 is 13. So there's the real part. Now let's look at the imaginary part. Outers are negative 6i plus 6i is 0. Okay. Now, haven't we run into something almost like this before? Where you have the sum times the difference of the same two numbers? Yeah, remember a plus b times a minus b? Y'all remember that, don't you? A squared minus b squared. Those are conjugates of each other, right? A plus b, a minus b, conjugates. The first numbers are the same, the second numbers differ only by the sign. You've dealt with them before, you've used them before, when you factored you used them, all sorts of places. These are what we call complex conjugates. They're complex numbers with opposite signs in the middle. The first numbers are the same, the second numbers are the same except for the change of sign. And whenever you multiply two conjugates together, you always get a real number. And that real number is the square of this one plus the square of that one, because the I squared becomes minus 1, so it's 9 plus 4 is 13. Always. Okay, not always 13, but always the sum of those squares. Okay, whereas the complex conjugate multiplied by each other of real numbers gives you the difference of their squares. For complex numbers, you get the sum of the squares of the real parts. Okay? And they carry you through all this and all that, and finally get to 13. Good for them. And that's in standard form, because it's 0i. Okay. Now, what if you square a complex number? Would you expect to get a real number, a complex number, or a pure imaginary number? That, unfortunately, is going to be back to being complex. And you just FOIL it. You just write this 2 plus I, 3 plus 2i squared is 3 plus 2i times 3 plus 2i. That's what it means to square a number. Let's do the real part. 3 times 3, 9. let's do the complex part, complete complex. That would be what? A little louder. 4i squared? Okay. And what's I squared? -1, so that'd be -4. So 9 minus 4 would be 5. That's the real part. Now let's do the imaginary part. 6i plus 6i is 12i. So, how does this work? Really just like the other one did. The square of the first, twice the product of the two, square of the last. But the square of the last is always going to be -4 on this one. Okay? I'm sorry. Square of the, it would be -4. So that's 9 minus 4 is the real part, and plus 12i is the imaginary part. So 5 plus 12i. Shorthand way to do it, if you want to do it like square the first, that gives you the 9. Square the last, that gives you, twice the product of the two, that gives you plus 6i, double that is plus 12i. Square the last is -4. So 9 minus 4 is 5 plus 12i. So, again, you're not responsible for this, but now you know how to do it if you ever need it. All right, I've already told you what complex conjugates are. Now they're going to tell you. In example 2c, which we just did, the product of two complex numbers can be a real number if those two complex numbers are complex conjugates of each other. That occurs when the pairs of complex numbers are of the form a plus bi times a minus bi. Those are called complex conjugates. Anytime you have same first number, opposite second number, in a pair, in binomial two, you have pairs of numbers, those are conjugates of each other. If they're complex numbers, those are complex conjugates. And they always turn out being, like we said, a squared. And this would be minus b squared, I squared, but I squared is -1, so that's plus b squared. And then the innards and the outers add to 0. abi minus abi is 0. So it just comes out a real number, and it's the sum of the squares of those real parts. The real part of the real number part of each, and the real number part of the complex part. That's weird, of the imaginary part. All right, now we get to how to do a quotient. What if we're trying to divide two complex numbers? A plus bi divided by c plus di. I don't know how to do that. I don't know how to divide this because I can't divide using imaginary numbers. I can only divide real numbers, okay? So what we do is multiply that denominator by its complex conjugate. That's going to make the denominator a real number, right? And then, but if you do that, you have to multiply the numerator by the denominator's complex conjugate. So I wish they'd have put parentheses here too. That would have made it look better. And here too. All right. Now that messes up your numerator big time, okay? It's now a times c, and then do the imaginary parts. That would be plus bd, because you're minus bdi squared, but I squared is -1, so it's plus bd. There's your real part. And your complex part are bci minus adi, so bc minus adi. Don't remember these letters, that's not important. It's how you do it. But what does that denominator become? Oh, that's much better. C squared plus d squared. Because that's how, when you multiply a complex conjugate, a number by its complex conjugate, you get the sum of their squares. Okay? Now, this is just a number. Okay? It looks complicated, it's just a number, a real number. This is just a real number multiplied by I. Well, this is just a number. C squared plus d squared is just a number. So you put this fraction, this number over that number, that's the real part, plus this number over that number, that's a fraction, times I, there's the complex part. So You can always write the quotient of two complex numbers as a complex number. Here's they're going to do it with actual numbers in there, which I wish they'd have put parentheses here because that's a little misleading the way they write it like that. Okay? Now, I'm not going to keep saying I'm not going to do them, but let's do what you get here. 8, and this part gives you minus 6, because I squared is minus 1. 8 minus 6 is 2. Okay, that's your real part. Your complex part, or your imaginary part, is 12i plus 4i is 16i. So 2 plus 16i, that's in the numerator. The denominator is what? 16 plus 4. 16 plus 4 is 20. So you have 2 over 20, which is 1/10, plus, what did we say the other one was? 16 over 20, which is 4/5 I. So something like that. 1/5 plus 4/5 I think that's how it came out. See, by multiplying by the complex conjugate, you make the denominator a real number, and then you can divide. Now put it over each part. 2 over 20 is 1/10, and 16 over 20 is 4/5, so it's 1/10 plus 4/5 I. That is, in standard form, a complex number. Real part, imaginary part. Got it? Okay. Again, you're not responsible for this, just so you see how to do it. Now, here's where you're going to run into it, and that's why I want you to be able to see that. You can write any such number, like square root of minus 3, okay, in standard form by writing this as square root of minus 1 times the square root of 3, right? Square root of 3 times the square root of minus 1. Square root of 3 is square root of 3. Square root of minus 1 is I, okay? So this would be square root of 3 times I. Now, I don't like writing it that way, okay? I know the book does because they like to write it in standard form, but if you are being a little sloppy, not that I'm ever sloppy, okay, and I wrote this as square root of 3i, can you tell for certain whether that i's inside or outside the radical? It's hard to tell. So when say again, even in this form, it's a little hard to tell. So what I usually do, I write that as I root 3. I know that's not in standard form, but it's not ambiguous either. It tells me I times root 3. That's what this is saying, but I'm not sure. This one, I'm absolutely sure. So I'm not really hung up on always having on standard form if it makes it clearer to see. Okay? But they like to write it like that. Okay? Now, the principal square root of a negative number would then be the square root of a times I. Okay? If there's a negative number, if a is a positive number, positive real number, the principal square root of minus a would then be the square root of a, principal square root of a, that's positive, times the imaginary unit I. I would write that I root a, but the book does it this way. So be very careful when you're doing these that you do it right. Okay? Again, you're not responsible for this, but you will perhaps see it in the future. Okay? Now, if I told you to solve that, what would be your first inclination? Hopefully it would be, second. Oh, she goes right through the quadratic formula. I would always try to factor it first, right? But guess what? You're not going to factor that. It's not going to factor. So then, Rachel's absolutely right. Go to the quadratic formula. Now, anyone remember how the quadratic formula goes? You will need to know this, folks. Okay? How does the quadratic formula go? What do you first identify? A is equal to 3. B is equal to negative 2, c is equal to 5. Now what do you do with that knowledge? You write down the answer. What? Is it that easy? Well, it sort of is. You write down x is equal to. Now, anyone remember how the quadratic formula goes? Negative b plus or minus the square root of b squared minus 4ac. All divided by 2a. All right, good deal. Remember, we got that by completing the square of your standard form of your quadratic equation, and this is what it came out being. Kind of messy, but fill in the numbers and you've got the answer. Okay, what's your b? And what's minus b? 2. The opposite of negative b would be positive b. Then you got your plus or minus, the square root of, what's your b squared? I'll be glad to write it out if that's helpful to you. Let's do that. That'd be minus a minus 2 plus or minus a minus 2 squared minus 4 times 3 times 5. Okay, that's written out in gory detail all over 2 times 3. Okay? Oh, get out of there. Okay. So now let's do the actual math. Negative of negative 2 is 2 plus or minus the square root of negative 2 squared is 4. Now, here's where I stop, pause for a moment. First thing I do for this part here is count my negative signs. Okay, how many do we have? 1. So anytime that number of negative signs is odd, like 1 or 3, then this is going to be a minus here. Okay? If that was even, 2, that's the only option there, it's going to be a plus sign. So I always do that. Now I just multiply the numbers together. 4 times 5 is 20, times 3 is 60. Okay? It'll come back. Okay. Divided by 2 times 3 is 6. Okay? Ooh boy, what do we have? 2 plus or minus the square root of negative 56 divided by 6. Okay? Now, head scratching time. Let's take that negative 56 and do the square root. Oh, let's see. Sorry. Let's take the square root of negative 56 and let's look for things. Okay? First, that's going to be a square root of negative 1. We know what that's going to be, don't we? Okay? Now, that negative, the 56, now that you pulled out the negative 1, 56, do you see any perfect squares hiding in a 56? What are your perfect squares? Name them. 1's always there, so leave that one alone. 0's always, no, it's not there, so leave that one alone too. What's the next perfect square? 4 is a perfect square. Will 4 go into 56? Yes. How many times? So let's pull out a 4, square root of 4, and how many times will 4 go into 56? 14 times. Now, are there any perfect squares hiding in 14? No. 14 is 2 times 7. Those are both prime numbers. Can't possibly have it. So, what we have here is now, and this again is how I like to write it. The book doesn't like this. The square root of 4 is 2i times root 14. Book doesn't like that at all. Okay? They're going to call that 2 root 14 times I. But I don't like following I after a radical because my writing is sloppy. Nobody else has sloppy writing, do they? I write it like this. Same difference. It's just what. So let's see what they got. I said I wasn't going to do this, but I wanted a review of the quadratic formula because we're going to be using it. So you see what our answer we got? Oh, no, we didn't. We didn't finish the problem. This is just the square root of negative 56. So what do we have? The answer is 2 plus or minus 2 I root 14. Now that is a weird way to write it, but I'm going to write it that way. I'm going to take this off of there. Over 6. Now I can simplify that just a little bit. 2 over 6 is 1/3 plus or minus, and 2 over 6 is 1/3 again, so that would be I root 14. The book doesn't write it like that, over 3. There's your two solutions to that quadratic equation. One of them is 1/3 plus I root 14 over 3, and the other is 1/3 minus I times root 14 over 3. The book writes them differently, as you will see, but I like to write them that way so it's not confusing about where that I is hiding. Okay, so let's just go through this quickly. There's the quadratic formula. They didn't write it down for you, but that's what we plugged it in to be. They got the same answer we did. Then they did this just like we did, 2 plus or minus 2. They put root 14I, which is okay when they print it and you can tell that radical doesn't extend over the I. That's fine. I don't like it, but it's fine. And that's the same as 1/3 plus or minus root 14 over 3 times I. Oh, that's the end of the section. Wasn't that fun? Okay. Now, you don't have to do any of the homework exercises here. You want to do vocabulary? It's up to you. Yeah or no? No. Okay, I'm all in favor. Okay. So let's move on to the next section, which is really an important section. Okay? And this is zeros of polynomial functions. This is really what the first 3 sections and that 4th section were building up to, finding the zeros of a polynomial function. That's usually the things that interest us the most. I don't know why PowerPoint is slow coming up. How are we doing on time? We've still got 18 minutes. All right. So let's get 18 minutes into 2.5. Come on. Oh. We tried to lock you out, but okay, don't pull it all the way. You were already here, right?
Yes.
Okay, so I got you in the book. You did it to yourself, didn't you? All right. Okay. So let's go from current slide. Now, are y'all getting ready to leave? Okay. Before we go, remember what we had to do today. Decide on a time to make up for Tuesday's class. Okay? Now, I gave you all the times. Let me go here. Let me get my pen set up. Okay. Let's do Monday, 8 to 10, or 3:45 to 6, either one of those. Tuesday, 9:45, that's right after this class, to 11:30, or 12:45 to 3:15. Plenty of time in there to do one. Wednesday is only 8 to 10. Okay, I don't have the afternoon slot. Thursday is just like Tuesday. I won't write it again, just like Tuesday. Okay? And then Friday is 8 to 12. Not tomorrow. I'll have to leave by 11 tomorrow, but we can do 10 o'clock scholar. Okay, good deal. Oh, yeah. Yeah. The weather is just miserable out there. Okay. But here is Tyler Kaiser. Okay. Now, I know we don't have a full class here, but y'all are the ones going to make the decision. Are any of these times better or worse than others? Let's just get a feel for it. How many can do either Monday or Wednesday, 8 to 10? 1, 2, 3, huh? I'm sorry.
I wouldn't be able to use my 8:30, but
Okay, Friday's the only time you could? Is that what you said? I can't hear.
Never mind.
Okay. Okay, how many can do Monday or Wednesday, 8 to 10? 1, 2, 3, 4, 5. Okay, is that all? Did I miss anyone? So that was 5 here or 5 here. Okay, Monday, 3:45 to 6. 1, 2, only 2. Okay, Tuesday or Thursday, 9:45 to 11:30. 1, 2, 3, 4, 5. No, you didn't. 5. Okay, so that's a 5 on both of those. And how about Tuesday or Thursday, 12:45 to 3:15? It's going to come back, I think. Okay. Tuesday or Thursday? Okay, 1, 2, 3, 3. Okay, how about Friday, 8 to 12? 1, 2, 3, 4, 5. Okay, how can it be this close? We got 4 possibilities that 5 people can come to. No, 5 possibilities. Okay, we got Monday, 8 to 10, Tuesday, 9:45 to 11. Well, both Monday and Wednesday, 8 to 10, Tuesday and Thursday, 9:45 to 11:30, and Friday, 8 to 12. Okay? Any of you have that can go any of those times? Rather not. I mean, you can do it, but you'd rather not do one of those times. Any? Second?
I didn't see which one.
Oh, any of them. Monday, 8 to 10. Monday or Wednesday, 8 to 10. Tuesday, Thursday, 9:45 to 11:30. Or Friday, 8 to 12. Now, second? What's that? Monday, Wednesday, and Friday. So you're out. Yeah. So, okay. But those who could do, there are one of those 5 in any of those. Is there any time that you'd rather not do? Even though you could do it, you'd rather not do it. Okay. So, what you want to do? You ready to do it right after this class today? We could. Okay. Okay, I know, but some people, the 5 people that can. Okay. Would you like to do it today right after this class? Or you want to do it tomorrow morning? Or Monday morning? Tuesday morning or Wednesday morning? Friday? Okay, do I hear mostly Fridays? Okay, yeah.
If we did it Friday, what time would it be? Because I have a meeting at 10 Friday.
Okay. Well then, and is it on this campus or the other campus?
Other campus.
This campus?
The other campus.
Other campus. So let's try to shoot for, if we do 8:30 to 9:45, would that give you time?
Yeah, I'll do that 10.
Okay, how about tomorrow morning, 8:30 to 9:45?
What?
Second? You don't want it tomorrow? Okay, not tomorrow, but next Friday. Next? Okay, wait, okay. No, well, you can't do it because you got biology
You're
class.
going to do it for 2 times?
No, only one class. We're going to make up one class. Okay? But I can't do it next Friday. Is next Friday the weekend of the 11th? I think it is. Yeah, 8th. Okay. I'm going to be out of town next Friday. So, the Friday after that? Or this Friday? You can't do it tomorrow? Cannot.
It's okay.
Okay. Let's go for tomorrow then. 8:30 tomorrow morning. You want this room or 255 or this room right here? Okay. Tomorrow morning, 8:30, I'll be here. And I'll have to be leaving after the class is over with. I got to go to the Birmingham campus also. Okay. So I think I do anyway. Say again? Tomorrow. Is that okay? I'll be recording it so everybody can pick it up. Okay. So y'all can go if you want to now. So tomorrow morning, 8:30, this campus, this room.
8:30 or 8?
What, you want to do 8? I just thought
8:30.
8:30 because classes usually don't start till 8:30. I'm going to be here by 8, but if you want to do, I just figured 8:30 would be when more people were used to coming here. Okay. All right, so let's do 8:30 tomorrow morning. will make up last time's class. So let's get started in the little time we have left. I don't even have my watch out, do I? How much time do we have left? Oh, we got 10 minutes, don't we? All right. Let me close the door because I do know my voice carries like a ton of bricks. Okay? Let's get started in 2.5. Now, I'll tell you this. What we do Friday is going to be continuing 2.5. And this is a pretty important chapter, so please watch the videos. Okay. So 2.5 is zeros of polynomial functions. What we're going to do in this is use the fundamental theorem of algebra to determine the number of zeros of polynomial functions. Hey, I thought we already knew that. No, we knew the maximum number of zeros, but this fundamental theorem of algebra tells us how many. It's not anything too new. Find the rational zeros of polynomial functions. That's going to be a new thing, but it's a really handy tool to have. We'll find conjugate pairs of complex numbers. We're going to kind of skip over that one because you're not responsible for the complex part. And we'll find zeros of polynomials by factoring. Okay? Then we'll use Descartes' rule of signs. That's going to be new for us, but it's a pretty simple thing. And the upper and lower bound rules. We'll find zeros of polynomials, and we'll find zeros of polynomials in real-life applications. Whew. As you can see, this section is going to take a while. It's got a lot of objectives. So let's get started right now, and mostly tomorrow we'll be continuing this. So let's start with the fundamental theorem of algebra. Ooh, that sounds impressive, doesn't it? In the complex number system, now we're leaving the real number system. Oh, we're still using it. Every nth order polynomial function has precisely n zeros. Okay? Remember before, we had, say, a quadratic function. We said the maximum number of zeros was 2. Now we say the actual number of zeros is exactly 2. But you see, before, we weren't counting complex. Okay? So now that we do count complex, we know there are exactly n zeros. Not the maximum, but we have n. This important result is derived from the fundamental theorem of algebra proven by this German mathematician Carl Friedrich Gauss. Boy, if someone hasn't chosen a paper topic, he would be a good one, because he was incredible, the stuff that he did. And not just in math, but also in physics. They actually named a unit of magnetism, because he did work in that after him. That's the Gauss, okay? In linear algebra, we solve matrices by the Gaussian elimination, okay? He was involved with that. All over the place. He lived after Newton, okay, and really expanded. Probably one of the greatest mathematicians after Newton who came along. Here's the fundamental theorem of algebra. Now, it sounds awfully simple, but to prove it was really difficult. If f of x is a polynomial of degree n, where n is greater than 0, of course, it has to be greater than 0. Can't be a constant, in other words, okay? Then f has at least 1 0 in the complex number system. Duh, yeah, of course, you would think it would have to have at least 1 0. So that doesn't sound that impressive. But what we got up above comes out of that. So using the fundamental theorem of algebra and the equivalence of zeros and factors, you can obtain what we call the linear factorization theorem. And here's what that says. If f of x is a polynomial of degree n, that's how we started every one of it, where n is greater than 0, so it's not just a constant. Because you see, if it's a constant, it doesn't have any zeros. Unless that constant is 0, and then every number is a 0. So that's why we leave off degrees greater than 0. Okay. Then f has precisely n linear factors. In other words, if you have f of x, a polynomial of degree n greater than 1, you have precisely, well, if it's degree 1, that is a factor. It's its only factor. If it's a quadratic, okay, if you can factor it, factor it. If not, you use the quadratic formula. That gives you 2 zeros. You can write them x plus one of those, x minus the other. The two that you get from the quadratic formula, those would be your two C's here. Where C1 and C2 and Cn are complex numbers. Understanding, remembering, real numbers are also complex numbers. Okay? So all of these could be real, some of them could be real, and some of them complex. It could be they're all complex, but that's really unusual, but it could happen. Okay? Well, they're all complex, but I have imaginary pieces to them. Okay. Note that the fundamental theorem of algebra and the linear factorization theorem tell you that only the zeros or factors of a polynomial exist, not how to find them. We've still got to do that. So these are called existence theorems. They don't tell you practically how to get them. So that's where we're heading next, is how in the world do we find these things? Okay, I can't get my watch. Being very uncooperative here. So let's do this one. For the first degree polynomial, f of x is equal to x minus 2, how many zeros does that have? 1. And what is it?
2.
X equal 2. Perfect. That is it. That's the only one. But what degree is this? You know how many zeros? All right. It works so far. Okay? Now, counting multiplicity. Remember, if you had x minus 2 squared, that would be x minus 2, x equal 2, and x equal 2. Counting multiplicity, the second degree polynomial function, this one, the two theorems we just did told you you have exactly 2 zeros. Can we determine what they are? What would you try first? Factor it. Let's see if we can factor that. Can we? That would be x times x. That's the only possible factorization for x squared. Look at the sign of the last term plus, what does that tell you these two signs have to be? They have to be the same, and since the middle sign's negative, they both have to be negative. Now, what's one possible factorization of 9? 3 times 3. Let's see if that works. Okay? Check it and see. X times x, x squared, that works. X times minus 3, minus 3x, minus 3x, minus 6x, plus 9. Yes, that works. So counting multiplicity, you have 2 zeros. X equals 3, and its brother x equals 3. Okay? It just happens to be the same number. That does count as 2 because it's a multiple 0. Okay? So sure enough, that works too. Let me erase this scratch and see how they did it. That's x minus 3 times x minus 3, exactly 2 zeros, x equals 3 and x equals 3. Called a repeated 0 of 3. Okay? How about a third degree polynomial? How many zeros you think it might have? 3. Let's see if we can find them. What would be the first thing you would do? Factor what? Factor out 1x, and that leaves you x squared plus 4. Can you factor any further? No. In fact, the sum of two perfect squares cannot be factored. It also is not a real number. Didn't say it could be a real number. It had to be a real number. Can anyone think what this number could be? I'm not going to give you these on a test, but can you think of what it would be? X is a factor. What could be the others? X plus 2i times x minus 2i. Remember, if you multiply a complex conjugate by a number by a complex conjugate, you get the sum of the squares. The sum of the squares of that is x squared. The sum of the squares of that is plus 4. You don't need to know that one, so don't sweat that one. Okay? But these are our two factors. Okay? Now, were they asking for factors or zeros? Where is it? Example 1, 3 zeros. So what are the zeros? x equals 0, x equal minus 2i, and x equal 2i. 3 zeros. Third degree, 3 zeros, there they are. Again, you're not going to be responsible for these kind because these have imaginary numbers. This is how you do it. Did that run us out of time? Okay. Let me clear the screen here so I can show you how they did it. Okay. Now, we'll start next time with the rational zeros test. Oh, yeah, and yeah. I'll do it in class tomorrow, okay? But it will be on the YouTube videos. Now, this is important stuff, folks. There's not many tests much more important than the rational zeros test, so be sure you watch the videos. If you can't be here tomorrow, be here, okay? If you can't be, be sure you watch the video, which will be up sometime, probably tomorrow afternoon. Hopefully. Good deal. Sorry I had to miss class last Tuesday. Yeah. Okay. All right. You forgive me. Wow, that makes me feel better. Okay, good deal.
Can I get a quiz and print off my essay?
Yeah.
Can I get a quiz?
Okay.
Can I go run my essay off and give it to you?
Absolutely. I'll be here for a few minutes, and I'll be down in room 255 for a few minutes, and I'll be in my office 265. Depends on how long it takes you.
Do you have a quiz with you right now?
Yeah, I'm going to give you the quiz right now. So I was just telling you when you come back, if I'm not in here, I'll be down. Okay? Oh, I'm in quiz 1. Quiz 2. Oh, there it is. You need graph paper?
Yes.
Okay, hold on just a second. There's a piece of graph paper.
Thank
All right, good deal. Anyone else need quiz 1? Okay. Oh, someone's going to turn in quiz 1. Multiplicity. That's what we were just talking about now. It has 2 roots, like x squared equals 0. That's x equals the one we just did. X equals 3 or x equals 3. That's a double multiplicity of 2. Where did you? Okay. All right. Go to that x squared.
Yeah.
2 squared.
Maybe you gave one for.
Anytime a factor is squared, that's a multiple root. And x squared, that's 2, yeah. The other 2 are 1 equal.
Oh, yes.
The book doesn't talk about multiplicity of 1, okay, but it does too. All right, good deal. Did you get your quiz? Yeah.
And they were just the same questions from the video.
Yeah, it's 20 out of 20.
That's it. Probably like you said.
You be trying to help people because
I'm thirsty. I'm running out of steam. Okay, Mari never showed up. Nigel never showed up. Good deal, thank you. Wrong. Jerry Cassidy didn't make it. Corey didn't make it. Maya didn't make it. Katie didn't make it. Charlotte didn't make it. Yoshi didn't make it. Amber. Stephanie. Charles. Emily. Okay.